And now for the exciting conclusion to section 4.3, evaluating trig extended circular functions. We left off yesterday finishing up this question, like I just said a moment ago before I started recording, being able to evaluate sine, cosine, and tangent anywhere we want on the xy plane by using x, y, and r instead of opposite, adjacent, and hypotenuse. We don't want to use terms like that anymore, especially when you're talking about questions like these three that we're looking at here, because these are quadrantal angles, multiples of 90 degrees. They don't even form triangles. How are you going to say opposite side when you're looking at a straight line, or hypotenuse when you're looking at a straight line? Doesn't make any sense. But as long as you're using x, y, and r to evaluate your sine and cosine, you will be just fine. That leads us to questions like this, and you have at least one of these on your test, I think maybe two. The directions are to solve for cosine of theta and tangent of theta using the information that you have there. First one says sine of theta is 3/7. Well, sine, just to remind you, sine is y over r. That means we have a positive y value and our radius is 7. The only problem with that is there are two quadrants where the y values are positive. Let's go ahead and draw those real quick. Which two quadrants have positive y values? 1 and 2. So I'm only going to draw the quadrants 1 and 2. I'm not going to bother with the down below. So this theta could have formed this shape, picture not drawn to scale. Or this one, which would just be a reflection into quadrant 2. Where y is 3 and r is 7. So there we have two different options for this theta. The second piece of information tells us that tangent is less than 0. That means tangent is negative. Well, tangent, if you recall, is y over x. So in which of those two quadrants, 1 or 2, will tangent, which is y over x, be negative? The one on the left, quadrant 2. So I don't even need to worry about quadrant 1. It's unimportant. So deuces, we'll just get rid of it. Okay. Clearly we're in quadrant 2 because it's the only place where you are going to have tangent be negative. We will need that x value, though, in order to evaluate cosine and sine. What do we know about the x value here? We know it's negative. Whatever we get for this answer, we have to use a negative length because we're in quadrant 2. Every point in quadrant 2 has a negative x value and a positive y value. Good old Pythagorean Theorem, x squared plus 3 squared equals 7 squared. Subtract your 9. And you're going to take the square root of both sides. 4 goes into 40. The square root of that is 2. So is x 2 root 10? No, what is it? Negative 2 root 10. All right. Because we're in quadrant 2, you cannot say x is 2 root 10. You must use the negative value, like that. If we were in quadrant 1, obviously, yeah, it would have been 2 root 10, not negative. Cool. We have our x, we have our y, we have our r. We can evaluate cosine and tangent now. Cosine of theta, which is, x over r, is going to be negative 2 root 10 over 7. Mr. M, shouldn't the negative sign be on just the top? There's no difference between the fraction having a negative sign on the front or the negative sign on the top. You know it's not on the bottom because the radius must be positive. Everybody cool with cosine? Yep. R is always the radius, which will always be the longest side length in the triangle. It's the hypotenuse. But because it's the radius of the circle, this circle, because it's the radius of the circle, it has to be positive because it describes a distance from the origin. And then what's left? Tangent. All right. Tangent of theta, we've already written on the slide up there that it is y over x. So it is negative 3 over 2 root 10. We don't need to rationalize the denominator. You can leave it like that. What do you think? It's like a little math puzzle, you know. The first piece of information tells you that you're in one of two places. The second piece of information is necessary in order for you to know where theta actually is. Ready to move? Awesome. Well, let's do it again. Secant of theta is positive 3. All right, well, secant is the reciprocal of cosine. And since cosine is x over r, secant of theta must be r over x. And sine of theta, meanwhile I'm here, is y over r. There. Cool. So secant of theta is 3. That is a fraction. What's its denominator? Yeah, it's 1. So what we have here is a radius of positive 3. Of course, the radius must be positive. And an x value of positive 1. There are two quadrants where secant would be positive because the x's are positive. Which two quadrants have positive x's? You could be louder. 1 and 4. So we go, all right, well, possibility of quadrant 1 or quadrant 4. We'll see which one it is. It's in one of those two. We know that it's either this triangle or this triangle. It's just a reflection across the x-axis. It's one of these two. And then you go, okay, well, which one of those is sign positive because the y values are positive? Quadrant 1, yeah. That means this down here was an impossibility, so we'll just not worry about that one, okay? There. We must be in quadrant 1. Secant is r. Oh, that didn't work. R over x. Well, we could get cosine right now. Cosine was free. It's the reciprocal of secant. You didn't have to work for that. Cosine of theta is just the reciprocal of 3 over 1. It's 1/3. There, that one was free. But in order to evaluate tangent, we will need to know the x value because tangent is y over x. So how do we find x again? Wait, excuse me, y again? Pythagorean theorem. Is y going to be positive or negative here? Positive. So at the moment you find y, just know, it's positive and I don't have to worry about a negative version. We go 1 squared plus y squared equals 3 squared. I was going to write 3 squared. Subtract the 1 from both sides. Take the square root of both sides. And the square root of 8 reduces to 2 root 2. And again, because we're in quadrant 1, we know it's positive. So we can find tangent now. Tangent of theta is y over x. They're both positive. Well, it's just 2 root 2 over 1. There it is. Hooray, Trig. Yes, ma'am. Which one are we talking, secant or the y values? Y values are negative in quadrants 3 and 4. For question A, yeah? What was negative? X value? Yeah, the x is negative because we're up here in quadrant 2. In quadrant 2, every point there is positive x, is negative x comma positive y. We're just talking about plotting regular old xy points. It has nothing to do with angles themselves. Just if you had to throw a point on a coordinate grid and I said, hey, -3, -1, you would hopefully know that goes in quadrant 3, where the x's and the y's are both negative. Okay. Yes, ma'am. Yeah? Yeah, because only positive numbers are greater than 0, yeah. So I won't say sine is positive or cosine is negative. I'll say sine is greater than 0, cosine is less than 0, things like that. Okay? Okay, so we called these things earlier in the lesson circular functions, but they can also be called periodic functions. What that means is they just repeat themselves every so often. Every so often they completely restart. Now for sine and cosine, I hope it's obvious why they repeat every 2 pi. And that's because, well, turning 2 pi is turning 360 degrees. That's a full circle, which is basically the same as doing nothing, right? So can we all agree to sine and cosine that going all the way around the circle is essentially the same as not moving? Is that okay? Okay. Now tangent's a little bit different. Because tangent is y divided by x, it's going to get every possible positive value in quadrant 1 and every possible negative value in quadrant 2. Then in quadrant 3, where both the x and the y are negative, tangent's positive again, which means quadrant 3's values are just copies of quadrant 1. And in quadrant 4, where only one of the letters is negative, tangent must be negative, it's just going to be a copy of quadrant 2. So because of that, tangent actually repeats itself every single pi, just because it uses the x's and the y's. Sine and cosine, and obviously because of that, they're reciprocals, but don't worry too much about it. Sine and cosine need 2 pi to repeat. Tangent only needs a single pi to repeat. And before I even start a question, can we all agree that turning 2 pi is essentially turning 0? Because 2 pi and 0 are coterminal angles. Everybody agrees with that? Okay. What that means is every time I see a multiple of 2 pi, I'm just going to cross it out and call it a 0 for sine and cosine. And every time I see a multiple of a single pi for tangent, I'm just going to cross it out because it's essentially the same as 0. That allows us to evaluate really large, or like part A, or really weird like part B, values of trigonometry without a cosine, simply by using periodicity. So we have sine of something ridiculously big. Can we agree that 1201 pi over 2 could be split into 2 fractions? Could be split into 12, I wrote 12, I said 12 and wrote 10. 1200 pi over 2 plus 1 pi over 2? Are we okay with that idea? Well, isn't 1200 divided by 2, well, that's an even number, right? That's sine of, come on now, 600 pi, which last time I checked is a multiple of 2 pi, plus pi over 2. And since 600 pi is a multiple of 2 pi, it's essentially the same as going nowhere. So it doesn't matter. It doesn't affect the outcome. If you would like to spin 300 circles, you are welcome to. But bet money, at the end of 300 circles, if you still have the ability to stand, you'll be looking the exact same direction that you started. That means sine of 1201 pi over 2 is equal to sine of pi over 2. So we just evaluate sine of pi over 2, and we are finished. And pi over 2 is 90 degrees. It's right there. Let's put a point right there. And here's our radius. So we need coordinates at that point. Tell me, what's the x value of that green dot that I put there? Oh, it's 0. Oh, okay. And what do we know about the y value? It's positive. And it's what? Well, yeah, but it's positive, not negative. So I'll just say 0 comma y. Now, if we were saying that that green line is the radius of a circle, you don't need to draw it, I'm just showing you. If it was the radius of a circle, what would the length of that radius be? It would be the length of y. Sine then, which is y over r, is whatever the y value is divided by whatever the r value equals. Sine of all that mess up there is just 1. Yes, Ashley. It's supposed to be y over r, correct? But r is y. Is that if that's confusing, then instead of saying positive y, just say positive 1. You could call that point 0, 1 if you want to. It won't matter. You call it 0, 5 if you want to. It won't matter because the radius would still be 1 or the radius would still be 5. So it actually doesn't matter. If the letter makes you uncomfortable, just pick a value for y and you'll still get the right answer. Okay? Well, it can't be 0 there because you're up on the y-axis. Because if y was 0 and x was 0, we'd be at the origin. And that's not an angle. Can I shrink it so I have more writing space? Okay. This was giving me trouble earlier. Let's see if it'll let me do it this time. All right. It's good because for the video, I want it to work right. Cool. The next one. Let me tell you, no, you cannot just subtract 20.45 from 28.45. No, you can't do that. Cosine's an operation. Let me demonstrate. Don't write this. Let me demonstrate to you why you can't do that. Does this equal 1? Of course not. See, cosine is acting kind of like a square root bar. It's an operation being performed on a number. You can't just subtract willy-nilly the arguments. You can't do that. It's not allowed. Okay? First period was like, oh, so no, no, no. I know that we want to do it, but that's just not how math works sometimes. Most times. In fact, the only time I can think of where you get to actually combine things in the argument because of addition and subtraction is logarithms. That's the only time that ever happens. So what do we do then? 28.45 pi, oh my goodness. 20.45 pi, oh my goodness. But you know what? It is beneficial to realize, that 28.45 is 20.45 plus 8. So there's the first one. And the reason why I wanted to do that is because, as far as cosine and sine are concerned, 8 pi is equivalent to 0. So what you actually have here is cosine 0.45 pi minus cosine of 20.45 pi. Yes? 28 pi? Because then you would have 0.45 pi, and I don't know what cosine of 0.45 pi is. That's why. If you have to add or subtract weird values of trig, of weird pi's, then your goal here is to not have to even worry about what that value is. I don't know what cosine of 20.45 pi is, so what I needed was for that to disappear somehow because I can't touch a calculator. And what we end up with is saying, yeah, cosine of 20.45 pi minus itself, which I think is rather obvious that it's 0. Neat, huh? Neat. All right. Can I shrink it so I have more writing space? Okay. Not yet, he says. Okay, well, it's highlighted. Yes, ma'am. Yeah, B has a value of 0. Neat, right? Shrinking. Scoot that over because I needed space. All right. Tangent. You know what I like about tangent? Tangent repeats itself every pi, not 2 pi. So as far as tangent is concerned, every multiple of pi is equivalent to 0. So I can just walk right over here and do this. Because 9 pi essentially is 0 as far as tangent is concerned. That means nothing. This is equivalent to tangent of pi over 4. So we just need to draw that. Picture not drawn to scale. How many degrees is pi over 4? 45. I like my special right triangles have degrees in them. I don't know why. I just think maybe it's because that's what we learn in geometry. So 45 degrees. And what classic side lengths do we use for the 45, 45, 90? 1 for the legs. Yeah, 1, 1 root 2. You're getting too technical on me, Kelly. Technical is her middle name. Kelly, technical, correct. Okay. Tangent's y over x. So what is it? Yeah, it's 1 over 1. Boom, done. And have fun. Is that the end of that page? Cool. I'd like you to go back a couple pages now to this table down here. Come on, come on. Let's get there. This was the table where we actually learned about x, y, and r. This is the table. And I can't remember if I said it to this class period or not, but I know I said it to at least one of them that I said, because of x, y, and r, we can write any point we want that's in the xy coordinate plane in terms of trigonometry. You see over there on the blue ray where it says point x comma y. When you come over here to these two things, that first one, sine theta equals y over r, if you multiply both sides by r, what you get is y equals r sine theta. And for cosine theta being x over r, if you multiply both sides by r, you get x equals r cosine theta. That means that every single x comma y point, no matter where it is in the xy plane, could be written as r cosine theta comma r sine theta. Isn't that neat? The answer is yes. So neat. You'd be surprised how often it's beneficial to use trig for coordinates than it is to use what we call rectangular coordinates. Rectangular means x, y, because they form boxes, you know. I got a question for you though. How big is the radius in the unit circle? Oh. Well, if the radius is 1 in the unit circle, then we just get this box. It's the same exact box, except for every time I would have written r, it equals 1. So no, sine is not y over r, sine is y over 1. So sine is y. And cosine is not x over r, cosine is just x. So in the unit circle, and only the unit circle where the radius is 1, every single point can be written as cosine theta comma sine theta instead of r cosine theta, r sine theta, because r is 1. So y is sine theta, x is cosine theta. And I'm going to pause the video for a moment because at this point, I usually have someone that sees something very interesting because of the results that we just found. So I'm going to pause the video while you guys try to figure it out, and then I'll reveal in a moment. This way the video is not ridiculously long, me telling people they're wrong.
What is it?
I'm going to tell you now that I've unpaused. I think I've unpaused it. Yeah, I'm recording again. So now that I've unpaused it, and we've had lots and lots and lots of think time and failure. Let me tell you something that's very interesting that somebody normally sees. I just told you that y is sine of theta and x is cosine of theta. That means tangent to theta is sine theta divided by cosine theta. What do you mean, well, yeah? You didn't say it, you didn't know it. Oh, yeah, you just know that, huh? Oh, yeah, it's just so obvious. Yeah. There you go. This is your first trig identity. Because in the unit circle, y is sine of theta and x is cosine theta, tangent of theta is equal to sine theta cosine theta, and it doesn't matter if you're in the unit circle or not. That's always true. So if Sean knew that, he should have said something.
No, he did, but I guess I wasn't paying attention to it.
Why'd you say it to him? You say it to me so I can praise you on YouTube. As it is right now, I don't believe you. Okay. There are a lot of trig properties to come, a lot of trig identities. That's your first one. But we're done with trig identities for today. I would like to reintroduce you to this unit circle now. I said you don't need to memorize it. I don't memorize it. Here's what I do. I know the 30, 60, 90 triangle. I know the 45, 45, 90 triangle. And I know the 30, 60, 90 turn on a side, 60, 30, 90. And all you have to do is reflect those triangles around the axes, and you can build the entire unit circle when you need it. I don't know what cosecant of 15 pi over 6 is off the top of my head. I don't need to. I can just reduce the fraction, figure out that it's a 30-degree angle because I said over 6, and draw that 30, 60, 90 where I needed to, and I can evaluate. I don't care if it's not as fast as memorizing all this. I'm not trying to memorize all this. I mean, just think about it. For every piece of data that's on this circle, imagine I had to forget one of your names in order for me to know it. You think there's 60 pieces of data up there? Because I only have 60 pre-calc honors or pre-calc advanced students. No, I'm not trying to remember all that. I know 3 triangles, and I know where x's are positive and y. You know x, y, and r for sine, cosine, tangent, and you're set. Which brings us to these last examples. Unfortunately, one of them is in degrees. Hey, but you know what? No system is perfect, so we'll have to do one in degrees. We're going to evaluate these without a calculator using our knowledge of special right triangles and periodicity. 15 pi over 4. That is remarkably close to a whole multiple of pi's. It's almost 16 pi over 4. It's literally a pi over 4 less than 16 pi over 4. So where is 4 pi is the question. 0, 2 pi, 4 pi. So this is where I would find 4 pi. All I have to do is go a pi over 4 less than that, which puts me here in quadrant 4. And because the denominator is a fourth, I know that the size of my reference angle is a pi over 4, which in degrees is 45 degrees. So I have a 45-degree angle, reference angle, I should say, 45-degree reference angle down there, and we fill out 1, 1 root 2, but I'm in quadrant 4. Y value is negative. Sine is y over r. Negative 1 over root 2. Radians beat the crud out of degrees. I don't know what 15 pi over 4 is in degrees. And I would struggle to know what quadrant it lands in, even if I did know what that number is. But I know real fast that 15 pi over 4 is right there. Radians are our friends. Or if you are not very good at seeing the whole 16 pi over 4 minus a pi over 4, you could have said that 15 over 4 is 3 and 3/4 if you wanted to, because this over here would be pi and 3 pi. Nope, knew that was going to happen. What's happening right now? So if that's 3 pi, you would then have to go another 1, 2, 3/4. But you land in the same spot. So either subtract away from 16 pi over 4 or add to, what, 12 pi over 4. It doesn't matter. Just pick one. Yeah. Because the over 4 means I'm dealing with fourths of my pi's. Pi is 180. 180 divided by 4 is 45. Can I shrink it so I have more writing space? Okay. Jokes. Hold on. There. Oh, it shrank my answer too. Oh well, we'll just do that. There. Next is cosine of 660 degrees. Ew. I'm sorry? It's 300 less than. Wait, someone just said something I absolutely love. They just said, can't we convert it to radians? I seem to remember a couple days ago, heels being dug into the sand about using radians over degrees. I know, I'm just saying. I love it. Look, would radians be easier here? Yes, they would be. But here's how you can do this. You can either say it is 300 degrees past 2 pi, which is 300 degrees past 360 degrees, or you could realize that 360 times 2 is 720. Either way, it's 60 degrees before 4 pi. So you can either think of it as saying that this is 360 degrees plus 300 degrees, or you could think of it as 720 degrees minus 60 degrees. Either way, you're going to have the 660. And since it is 60 degrees before my 2 pi, once again, I'm in quadrant 4. Picture not drawn to scale, as usual. This time, though, what's the size of my reference angle? Yeah, it's 60. 60 degrees. What kind of value can always be found across from a 60? I didn't know what kind of side length. What, it's 1 root 3, 2. Which one's always across from the 60? The root 3. Because the 1 is always going to be across from the 30. But because I'm in quadrant 4, it's negative root 3. And you know what? That actually doesn't affect the answer because this is cosine. X over r. And x over r here is going to be 1 over 2. Switch colors for funsies. 2 is a radius. Radius can never be negative. X's and Y's can be negative. Radius cannot be. Because the radius represents the distance from the origin. Can I shrink it to get that last quote? Yes? Yes, the reference triangle. So if you went the full 360 degrees, which obviously gets you back to 0, and then you go 300 degrees, you're using what's left over, which is 60 degrees, as a reference to get your side lengths on there. Okay? Yes? Because, okay, let me ask you, what's bigger, 1 or the square root of 3? Square root of 3 is bigger, right? In geometry, you learned something called the triangle inequality theorem that says that long sides are across from large angles. So because 30 is the smallest angle, it has the shortest side across from it. Can I shrink it? And then there was 1. 8 pi over 3. You know what's neat about tangent? It repeats itself every pi. So we don't even need that to get to a multiple of 2 pi. We just need it to get to a multiple of pi. So what's the next multiple of pi? 9. Well, 9 pi over 3. Because 9 pi over 3 is 3 pi, right? 9 pi over 3 is 3 pi. That means my angle of 8 pi over 3 is a pi over 3 before 3 pi, which puts me in quadrant 2. Because this would have been 0, pi, not 0, sorry. It would have been pi and 3 pi. 0's over here. So we are a pi over 3 before, because, 9 pi over 3 minus 1 gives me 8 pi over 3. We are a pi over 3 before 3 pi, landing us here. As usual, picture not drawn to scale. What I need to know is, what is the size of my reference angle? 60, because pi over 3 equals 60. So I have a 60-degree reference angle, and in the last example, we said that across from a 60 will always be a root 3. In quadrant 2, is that root 3 going to be positive or negative? Yeah, it's positive. And in quadrant 2, for this triangle, is my x going to be positive 1 or negative 1? Negative 1. Radius is 2. And tangent is, it doesn't matter what my theta is. Tangent of theta is always y over x. So tangent at our theta is negative root 3. It's, yeah, y over x. Cotangent is x over y. It's y over x. That's it, guys. Fiend. Nice.